Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently toward one of the smallest ideas in all of physics, the Planck length. For now, imagine a quiet room at night. A lamp is glowing beside you. A chair rests on the floor. A book lies open on a table. Everything appears solid and still. Yet if we could move inward, not with hurry but with patience, the surface of that ordinary room would begin to open into hidden layers. Wood would become molecules, molecules would become atoms, atoms would become nuclei and electrons. Nuclei would become protons and neutrons. Protons and neutrons would become quarks, held inside fields whose behavior is already far from the everyday world. And then the question becomes stranger. If we keep going inward, does nature simply keep giving us smaller and smaller distances forever? Or is there a point where the very idea of a distance becomes uncertain? Not because our instruments are clumsy and not because our microscopes are weak, but because space itself may no longer behave like a smooth stage on which objects sit. That is the quiet mystery of the Planck length. It is not a tiny ruler mark chosen by humans. It is not just a very small number with a famous name attached. It is a scale built from the constants that seem to hold together relativity, quantum mechanics, and gravity. It is the place where our best maps begin to overlap so completely that the paper tears. So tonight, we will travel down through matter, into the birth of quantum theory, into the constants of nature, and toward the strange frontier, where measurement itself may begin to make black holes instead of answers. Tonight, we are going somewhere smaller than any distance you've ever thought about. Smaller than atoms, smaller than the particles inside atoms, smaller than anything a microscope or any instrument ever built has come close to seeing. We're going to the place where space itself runs out of meaning, where the idea of distance stops working. Not because our tools fail, but because the universe itself has a limit, a deep floor beneath everything that exists. This place has a name, the Planck length. And by the end of tonight, you are going to understand why physicists believe it is the smallest meaningful distance that can exist in our universe. Why our best theories stop fitting together cleanly at that scale, and what that tells us about the true nature of space and time. Everything you can see right now is made of something smaller. The chair you are sitting on is made of molecules. Those molecules are made of atoms. The atoms are made of nuclei surrounded by electrons. The nuclei are made of protons and neutrons. The protons and neutrons are made of quarks. And the quarks, as far as we can currently tell, are fundamental particles with no internal structure, no known smaller components, no subquarks, no deeper level that any experiment has yet managed to reach. Here is the question that still draws theoretical physicists back to the blackboard. Is that actually the end? Or does it keep going? And if it keeps going, does it go on forever? Or does it eventually hit a wall? For most of the history of science, these questions were purely philosophical. You could ask them, but you had no physical way to approach an answer. The tools of physics simply weren't sharp enough. Then in 1900, a German physicist named Max Planck published a paper that would quietly become one of the most important in the history of science. Not because of what he discovered about the specific problem he was solving, because of what he noticed almost incidentally about the numbers buried inside the solution. Planck was working on the problem of black body radiation. This is the light emitted by any object based purely on its temperature. Regardless of what it is made of, a hot piece of iron glows red, hotter still. It glows orange, then yellow, then white. The exact spectrum of light that an object emits depends only on its temperature, not its material, not its surface, not its history. Just its temperature. This was a well-established experimental fact by the late 19th century. But classical physics couldn't explain it. The equations of 19th century physics predicted that hot objects should emit infinite energy at short wavelengths. Blue light, ultraviolet light, X-rays, gamma rays, all of it should pour out of any warm object in unlimited, impossible quantities, which was obviously wrong. Hot objects do not pour outward in a burst of infinite radiation, they just glow. This failure had a name, the ultraviolet catastrophe, and it wasn't a minor discrepancy. It was a fundamental breakdown. Classical physics in the regime of very short wavelengths was simply wrong. Planck solved it by introducing what he himself years later described as an act of desperation. He proposed that energy is not continuous. It does not flow in smooth, infinitely divisible streams. It comes in discrete packets, tiny indivisible chunks. He called them quanta. The energy of each packet is proportional to the frequency of the light, with the proportionality constant being a new fundamental constant of nature. That constant is now called Planck's constant, written as h with a value of approximately 6.626 times 10 to the power of minus 34 joule seconds. The formula worked. It fit the experimental data perfectly. But the formula introduced something that Planck found genuinely disturbing: the discreteness of energy. The idea that there is a minimum amount of energy you can have at a given frequency. You can have 1 quantum, or 2 quanta, or 3, but not 1.5. The world at this level is not continuous. It comes in chunks. And Planck trained in the tradition of 19th century physics, where everything was smooth and continuous, spent years trying to find a way around this conclusion. He couldn't. The quanta were real. But what he noticed in the margins of the calculation matters most for tonight. He observed that his new constant h, combined with two other fundamental constants of nature, the speed of light and the gravitational constant, produced something remarkable. A natural unit of length, not a unit chosen by humans for practical convenience. Not a meter defined by the circumference of the Earth or the distance light travels in a specific fraction of a second. A unit derived entirely from the deepest constants of nature, from quantities that, as Planck himself noted, would be the same for any civilization anywhere in the universe. He called them natural units. We now call the length one the Planck length. The calculation is worth understanding in its structure. You take Planck's constant ah divided by 2 times pi. Physicists write this as h bar, the reduced Planck constant. Then you multiply by Newton's gravitational constant g, approximately 6.667 times 10 to the power of minus 11 meters cubed per kilogram per second squared. Then you divide by the cube of the speed of light, approximately 2.998 times 10 to the power of 8 meters per second. This is one of the themes of the journey. Every time physics reaches a new scale, familiar words keep working for a while. And then they begin to ask for new meanings. You take the square root of the whole expression. The result is approximately 1.616 times 10 to the power of minus 35 meters, written out fully. That's a decimal point followed by 34 zeros, then the digits 16. To appreciate this number, you have to work your way down through the sizes of things we actually understand. A human being is roughly 1.7 meters tall. A human hair is about 80 micrometers wide, roughly 8 times 10 to the power of minus 5 meters. A typical bacterium is about 1 micrometer across 10 to the power of minus 6 meters. A virus is smaller still, perhaps 100 nanometers, 10 to the power of minus 7 meters. A water molecule is about 2.8 times 10 to the power of minus 10 meters. A hydrogen atom is about 53 picometers, roughly 5 times 10 to the power of minus 10 meters. The nucleus of a hydrogen atom, a single proton, is about 85 times 10 to the power of minus 18 meters across. And the Planck length is roughly 10 to the power of 20 times smaller than that proton. A single proton relative to the Planck length is roughly the same scale as the entire observable universe is relative to a proton. The proton sits almost exactly at the geometric midpoint between the observable universe and the Planck length. We live as a species at a scale very close to the center of the knowable range. That's not a coincidence in any deep sense. It is just how the numbers happen to work out. But it does put our position in the cosmos in a new kind of perspective. The Planck length is not just small. It is small in a way that stretches the imagination past its breaking point. And what makes it fundamental is not the size. What makes it fundamental is what it represents. To understand that fully, you need to understand what these three constants actually are. Not just their numerical values, their physical meaning. The speed of light is the most universal constant in physics. It is not just the speed at which light travels. It is the maximum speed at which any physical influence can propagate through the universe. Nothing with mass can reach it. Massless particles travel at exactly this speed. Information cannot be transmitted faster. The speed of light is built into the geometry of space-time itself. In special relativity, space and time are not separate independent dimensions. They're aspects of a single unified entity. And the speed of light is the conversion factor between the space dimension and the time dimensions. 1 second of time is equivalent in the language of special relativity to approximately 300 million kilometers of space. This equivalence is why the speed of light appears everywhere in electromagnetism, connecting electric and magnetic fields in the mass-energy equivalence of special relativity. In quantum field theory, connecting the frequency of a quantum field to the energy of the particles it describes. In general relativity, determining how quickly gravitational influences propagate, it is not a property of light in particular. It is a property of space-time. Light just happens to travel at that speed because light is mediated by the electromagnetic field, which is massless. And all massless fields propagate at the speed of light. The gravitational constant g is different in character. Where the speed of light sets, the geometry of space-time g sets how strongly that geometry responds to matter and energy. A massive object curves the space-time around it. How much it curves depends on g. In a universe with a larger g, gravity would be stronger. Stars would form more easily, burn faster, collapse sooner. Planets would need to orbit closer to their stars to maintain stable orbits. In the quiet language of this episode, that is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. The structure of the universe, from the formation of the first stars to the evolution of galaxies, would be profoundly different. The particular value of g in our universe, approximately 6.67 times 10 to the power of -1 in SI units, is what produces the universe we observe, including the conditions that allowed life to arise here. Planck's constant h is the constant of the quantum world. Its value sets the scale at which quantum effects become important. For a swinging pendulum or a baseball or a planet, quantum effects are utterly negligible. The uncertainties introduced by quantum mechanics are so many orders of magnitude smaller than any practical measurement that they do not matter. But for an electron in an atom, or a photon of light, or the vibration of a molecular bond, quantum effects are everything. They determine the energy levels of atoms, the wavelengths of light that atoms emit and absorb, the stability of chemical bonds, the electrical properties of materials. Without Planck's constant, atoms would collapse. Electrons would spiral inward and fall into the nucleus in a non-cond. Matter as we know it wouldn't be stable. Planck's constant is what holds the quantum world together. Now, combine all three. The speed of light, which governs the geometry of space-time, the gravitational constant, which governs how strongly that geometry responds to matter. and Planck's constant, which governs the scale at which quantum effects dominate. The combination produces a length at which all three of these fundamental frameworks, the geometry of space-time, the curvature caused by energy, and the discreteness of quantum mechanics all become equally important simultaneously. The important thing is not to imagine a hard little brick of space. The better image is a boundary in our understanding, a place where smooth geometry and quantum uncertainty can no longer be separated. At scales much larger than the Planck length, you can use general relativity for gravity and quantum field theory for everything else. And they do not get in each other's way. The domains are separate, but at the Planck scale, those domains overlap completely. Quantum fluctuations become energetic enough to curve space-time significantly. Gravity becomes important even for individual quantum particles. The two frameworks can no longer be kept separate. They must be unified. And that unification is precisely what we do not know how to do. The 20th century produced two transcendent physical theories, general relativity and quantum mechanics. Together, they describe essentially everything in the physical universe between them, covering 60 orders of magnitude of physical scale. And they are fundamentally incompatible with each other at the level of their basic assumptions. General relativity was completed by Albert Einstein in November of 1915, after approximately 10 years of sustained intellectual effort that he later described as the most strenuous work of his life. The basic physical picture is this: gravity is not a force. It is a consequence of the curvature of space-time. Mass and energy tell space-time how to curve. Curved space-time tells matter and energy how to move. This is the whole of general relativity in two sentences. But the mathematical content is far richer than those sentences suggest. The curvature of space-time is described by a mathematical object called the metric tensor, a 10-component field that encodes the geometry of four-dimensional space-time at every point. Einstein's field equations relate the curvature of the metric tensor to the distribution of mass and energy through a mathematical object called the stress-energy tensor. These are coupled non-linear partial differential equations. They're extremely difficult to solve in general, but in special cases, including spherically symmetric mass distributions, uniform cosmological models, and gravitational waves in empty space, exact solutions can be found. And each of those exact solutions has been tested against observation. The Schwartz solution, which describes the geometry outside a spherically symmetric mass, correctly predicts the bending of light, the gravitational red shift, the precession of planetary orbits, and the existence of black holes. The Friedmann-Lemaitre-Robertson-Walker solutions, which describe a homogeneous and isotropic expanding universe, are the basis of standard cosmology and correctly predict the large-scale structure of the observable universe. The plane wave solutions correctly predict the properties of gravitational waves confirmed by LIGO. General relativity works not approximately precisely. Quantum mechanics was built by a generation of brilliant physicists through the 1920s and 30s. Werner Heisenberg formulated matrix mechanics in 1925. Erwin Schrödinger formulated wave mechanics in 1926 and showed it was mathematically equivalent to Heisenberg's approach. Paul Dirac produced a relativistic version of quantum mechanics, the Dirac equation, in 1928, which naturally predicted the existence of antimatter. The positron, the antiparticle of the electron, was discovered in 1932 by Carl Anderson, confirming Dirac's prediction. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga independently developed quantum electrodynamics in the late 1940s, combining quantum mechanics with special relativity and electromagnetism into a single consistent framework. Quantum electrodynamics makes the most precisely verified predictions in physics. The magnetic moment of the electron predicted by quantum electrodynamics agrees with the experimentally measured value to 1 part in approximately 1.2 trillion. Over the following decades, quantum field theories for the weak nuclear force and the strong nuclear force were developed. The electroweak theory unifying electromagnetism and the weak force was formulated by Sheldon Glashow, Abdus Salam, and Steven Weinberg. The theory of quantum chromodynamics described the strong force. Together, these theories form the standard model of particle physics, the most comprehensive and precisely tested theory of matter and its interactions. But when you try to apply the methods of quantum field theory to gravity, the calculation falls apart. In quantum field theory, forces are mediated by particle exchange. Electromagnetism is carried by photons, the weak force by W and Z bosons, the strong force by gluons. So you try to build a quantum theory of gravity around gravitons, the hypothetical particles that would carry the gravitational force. The calculation starts off seemingly normal. You write down the gravitational interaction in a form similar to the electromagnetic interaction. You try to compute quantum corrections, the contributions from virtual particles and loops, and you find infinities. Not the innocuous infinities that appear in quantum electrodynamics and can be absorbed into redefined physical parameters through renormalization. These infinities are not renormalizable. Every order of perturbation theory introduces new infinities that require new free parameters to absorb them. At the one-loop level, you need to add certain terms to the action. At the two-loop level, you need to add more. At the three-loop level, more. Again, the theory requires an infinite tower of new parameters. With infinitely many free parameters, the theory can reproduce any observation, which means it predicts nothing. It is not a physical theory, it is a parameterization. This failure signals something important. The framework of quantum field theory applied naively to gravity is wrong at the Planck scale. Not approximately wrong, fundamentally wrong. The tools need to be replaced, and the replacement is what physicists have been searching for. Here is the physical argument for why the Planck length is the smallest meaningful distance. It is elegant, and it follows from first principles. The Heisenberg uncertainty principle says that position and momentum cannot both be known with arbitrary precision. If you know position to within delta x, the momentum uncertainty delta p must be at least h bar divided by 2 times delta x. Seen this way, the Planck length is less like the end of a road and more like a misty shoreline. The land behind us is measured space. The water ahead is quantum gravity. In quantum mechanics, a particle's wavelength is inversely proportional to its momentum. The more energy a particle has, the shorter its wavelength. To probe a distance delta x, you need a probe with a wavelength comparable to delta x. Smaller probe target requires shorter wavelength. Shorter wavelength means higher energy. So probing smaller distances always requires higher energy probes. This is not a technical limitation. It is a fundamental physical consequence of wave-particle duality. Now bring in gravity. Energy is equivalent to mass via E equals meters c squared, mass curves spacetime. More energy in a small region means more curvature. If you concentrate enough energy into a small enough region, the spacetime curvature becomes so extreme that the region becomes a black hole. Specifically, the Schwarzschild radius, the radius of a black hole of mass m, equals 2 g-meters divided by c to the power of 2. For a probe carrying energy E, the equivalent mass is E divided by c to the power of 2. So the Schwarzschild radius of our probe is 2GE divided by c to 4th. We want this Schwarzschild radius to be comparable to the probe's wavelength, which is h bar c divided by E. Setting them equal and solving for the length scale gives the Planck length. At this length scale, the probe would need so much energy that it would spontaneously become a black hole. The black hole swallows all the information you were trying to extract. In the quiet language of this episode, that is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. The measurement returns nothing. Any attempt to probe distances smaller than the Planck length necessarily creates conditions that prevent the measurement from returning useful information. The concept of distance at sub-Planck scales is not just unmeasurable. It may not exist in any physical sense. This brings us to quantum foam. John Wheeler coined this term in the 1950s to describe his intuition about what space-time looks like at the Planck scale. Wheeler was one of the central figures of mid-20th century physics. He worked with Niels Bohr on nuclear fission before the Second World War. He taught at Princeton for decades and supervised an extraordinary number of important physicists. He coined not just the term black hole, but also terms like wormhole, and it from bit the latter, expressing his belief that physical reality is fundamentally informational. In 1955, Wheeler wrote a paper in which he argued that the vacuum of space, far from being empty and featureless, must be in a state of violent quantum fluctuation at the Planck scale. The argument came from combining general relativity and the Heisenberg uncertainty principle. In ordinary quantum field theory, the electromagnetic field fluctuates. Virtual photons appear and disappear constantly. These fluctuations are real and have measurable consequences, like the Casimir effect, where two uncharged metal plates placed very close together are pushed toward each other by the vacuum fluctuations of the electromagnetic field between them. This effect has been measured experimentally to high precision. The gravitational field should fluctuate too, and fluctuations in the gravitational field are fluctuations in the geometry of space-time. In a region of size delta x, the uncertainty in energy is approximately AH bar C divided by delta x. This uncertain energy curves spacetime. The uncertainty in the curvature of spacetime over a region of size delta x is approximately the Planck length squared divided by delta x to the power of 2. When delta x is much larger than the Planck length, this curvature uncertainty is tiny. Spacetime looks smooth. When delta x approaches the Planck length, the curvature uncertainty becomes of order 1. The geometry fluctuates wildly. The very topology of space, not just its curvature, but its connectivity, may be uncertain. Tiny wormholes might flash into existence and dissolve. The geometry might split into separate regions and reconnect. What Wheeler called quantum foam, not a metaphor, a prediction from combining the uncertainty principle with the curvature of space-time. At the Planck scale, smooth geometry is replaced by a quantum superposition of wildly different geometries, all coexisting until something interacts with that region and collapses the superposition. The smooth space-time of everyday experience is a large-scale average, an emergent calm over an underlying storm. Loop quantum gravity is the most developed attempt to directly quantize spacetime. It was developed starting in the mid-1980s by Abhay Ashtekar and then extended by Lee Smolin and Carlo Rovelli and many others. The starting point is a reformulation of general relativity. Rather than working with the metric tensor as the fundamental variable, Ashtekar reformulated general relativity using connection variables. In this formulation, the theory looks much more similar to the other gauge field theories like electrodynamics and the theory of the strong force. And gauge theories are things we know in principle how to quantize. When Smolin and Rovelli applied the quantization procedure to Ashtekar's reformulation, they found something remarkable. The quantum states of spatial geometry are not described by a smooth manifold at all. They're described by spin networks. A spin network is a graph, a collection of nodes connected by edges. The nodes represent quantized chunks of volume. Each node carries a label, a quantum number that determines how much volume it represents. The edges represent quantized areas connecting the chunks of volume. We will keep the language gentle, but the idea itself is deep. At the smallest meaningful distances, the universe may not offer a smaller stage to stand on. Each edge carries a quantum number that determines how much area it represents. The area carried by an edge is given by a formula proportional to the Planck length squared scaled by a quantum number on that edge, and by a free constant in the theory called the Barbero-Emirzi parameter. The exact value depends on this free parameter, but the scale is set by the Planck area, roughly 1 Planck length squared. There is no area smaller than this. You cannot subdivide space below the Planck scale in loop quantum gravity because there are no finer grain spin network states. The minimum quantum of area is the Planck area. The minimum quantum of volume is the Planck volume, roughly the Planck length cubed. Space is discrete at the Planck scale, not approximately discrete. Not discrete in the sense that we cannot measure anything smaller. Discrete in the sense that there is nothing smaller. The spin network is the actual quantum state of space. Below its scale, there is no space. When you zoom in on a region of space in loop quantum gravity, you eventually reach a scale where you can count the nodes. 1, 2, 3. You can count the edges connecting them. The geometry is finite and discrete, not a smooth manifold, a graph. This is a profound conceptual departure from both general relativity and ordinary quantum field theory. Space is not the arena in which physics happens. Space is itself a physical system subject to quantum mechanics in a superposition of states with discrete excitations. Just like the electromagnetic field is not just a background for electrons to move in, but is itself a quantum field with its own excitations, which we call photons. The gravitational field is not just a background for other fields to live in. It is a quantum field with its own excitations, and those excitations at the Planck scale are the spin networks. The smooth space of everyday experience is not the fundamental reality. It is what you see when you zoom out far enough that the discrete spin network looks continuous. Like how a pixelated image looks smooth when you stand far enough back, the pixels are real. The smoothness is an illusion of scale. Loop quantum gravity also predicts a minimum time interval. The Planck time, roughly 5.4 times 10 to the power of minus 44 seconds. The universe does not evolve continuously in time. It evolves in discrete steps, each step lasting 1 Planck time. Between the steps, time does not pass. There is no in-between. There is the state at one step and the state at the next. The smooth flow of time that we experience is an emergent phenomenon, an average over enormous numbers of Planck time steps, like how the continuous motion of a film emerges from individual frames played rapidly enough. But the frames are real. The continuity is a perceptual illusion. At the Planck scale, the film stops. There are only frames. String theory approaches quantum gravity from a completely different direction. Where loop quantum gravity starts with the geometry of space and quantizes it, string theory starts with the matter content of the universe and asks what the minimum size objects look like. In ordinary quantum field theory, the fundamental objects are point particles. Electrons have no size. Quarks have no size. All particles are mathematical points. This works extraordinarily well at the energies we can probe. But point particles cause problems. When 2 point particles interact, they can be at the same point simultaneously. And the energy associated with a point interaction is infinite. You need renormalization to handle these infinities. For electromagnetism, the weak force and the strong force, renormalization works. For gravity, it does not. The infinities generated by point-particle graviton interactions are non-renormalizable. They cannot be absorbed into a finite number of redefined parameters. String theory proposes a minimal fix. What if particles aren't points? What if they're tiny, one-dimensional objects? Strings with a characteristic length, the string length, which is near the Planck scale. Two strings do not interact at a single point. They interact over a finite region because they have finite size. The interaction is spread out, and a spread-out interaction does not produce the same infinities as a point interaction. In string theory, the graviton is a particular vibrational mode of a closed string, a loop vibrating in the mode with spin 2. When you compute the interactions between gravitons in string theory, you find that the theory is finite. No non-renormalizable infinities, in the quiet language of this episode. That is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. The ultraviolet catastrophe of quantum gravity does not happen because the strings are spread out. The problematic short-distance behavior that produces infinities in point-particle theories is smoothed out. String theory works in 10 space-time dimensions, 9 of space and 1 of time. The extra 6 spatial dimensions are compactified, curled up into very small sizes near the Planck scale, so that they're invisible at the energies we can probe. T-duality, which we mentioned earlier, is one of the most striking features of string theory. In a space-time where one spatial dimension is curled into a circle of radius ER, string theory on that space-time is completely equivalent to string theory on a space-time, where that dimension has radius equal to the square of the string length divided by ER. If the string length is near the Planck length, then a circle of radius 100 Planck lengths is equivalent to a circle of radius 100th of a Planck length. The two are physically identical. Let us move through this slowly, because the smallness here is not only a matter of size, it is a change in what size can mean. You cannot distinguish between them by any string theory observable. This means that in string theory, the concept of smaller than the string scale is not physically meaningful. There is no observable distinction between very small and very large. Once you are below the string scale, the usual notion of distance of smaller and larger breaks down, not because of experimental limitations, because of T-duality. The string scale is where the concept of size changes its meaning. This is a genuinely different kind of breakdown than what happens in loop quantum gravity. In loop quantum gravity, space is discrete below the Planck scale. In string theory, space is still continuous, but the duality makes small and large equivalent. Two different mathematical pictures, both pointing to the same physical conclusion. Something fundamentally different happens at the Planck scale. The usual rules about distance stop working. There is another quantity worth dwelling on, the Planck temperature. Just as the Planck length is the smallest meaningful distance, the Planck temperature is the highest meaningful temperature. It is approximately 1.4 times 10 to the power of 32 Kelvin. At that temperature, the thermal energy of a typical particle is equal to the Planck energy. The conditions become so extreme that quantum gravitational effects dominate. Space-time itself is subject to such restless quantum fluctuations that our usual descriptions of temperature and thermal equilibrium cease to apply. For context, the surface of the Sun is about 5,800 Kelvin. The center of the Sun is about 15 million Kelvin. A stellar mass black holes. Hawking temperature is somewhere around 60 nanokelvin. The hottest temperatures achieved in particle accelerators are in the range of several trillion Kelvin. In the quark-gluon plasma created in heavy ion collisions at facilities like CERN and Brookhaven, Temperatures in the very early universe during the quark-hadron transition were around 2 trillion Kelvin. The Planck temperature is 10 to the power of 20 times higher than those accelerator temperatures. And it is the temperature at which the physics of the Big Bang epoch becomes completely intractable without quantum gravity. The universe passed through the Planck temperature in the first 5.4 times 10 to the power of minus 44 seconds of its existence. In those first moments, every cm of space contained energy at densities and temperatures that no current physics can describe. What happened at and before the Planck temperature is genuinely unknown, not approximately unknown. Unknown in the sense that no current theory provides any valid description. This is not a gap in our knowledge that could be filled by more experiments or more computing power. It is a gap that can only be filled by a fundamentally new theory. A theory that unifies quantum mechanics and gravity. A theory that can describe the conditions of the Planck epoch without producing mathematical nonsense. The Planck temperature, like the Planck length, marks the boundary of the knowable with current physics. Beyond it, on the other side of that boundary, is the beginning of the universe. And we have no idea what it looked like. The history of physics is not just a history of answers. It is a history of discovering the right questions. Aristotle asked the wrong question about motion and spent centuries getting the wrong answer. He asked, "What makes things move?" His answer was that objects seek their natural place. Heavy things fall because they seek the earth. Light things rise because they seek the heavens. This was the wrong framework. The right question was not what makes things move, but what makes things change their motion. That shift in the question from motion to change of motion was what Newton needed to formulate his laws. And once the question was framed correctly, the answer followed relatively quickly. The history of the atom followed a similar pattern. For most of scientific history, people asked what matter is made of. The answer kept getting reframed. Molecules, atoms, electrons and nuclei, protons and neutrons, quarks. Each time the answer seemed like the end, a new question emerged. What are those made of? The question of what lies below the quark, below the electron at the Planck scale, is the current frontier of that particular thread. And the answer may require changing the question again. Not just asking what the smallest particle is, but questioning whether the concept of particle is the right way to think about it at all. String theory replaces particles with strings. Loop quantum gravity questions whether space-time itself is fundamental. Other approaches question whether space and time are the right variables at all. Twistor theory, developed by Roger Penrose, starting in the 1960s, reformulates physics in terms of different fundamental objects called twistors, which are more naturally adapted to the causal structure of spacetime. In twistor theory, the points of spacetime are derived quantities. They're not fundamental, they emerge from more primitive objects. This kind of restructuring of what is fundamental is exactly what may be needed at the Planck scale. The universe at the deepest level may not be made of particles moving through space. It may be made of something else, something that produces the appearance of particles in space at larger scales. But that is different in character at the Planck scale. What that something else is, nobody currently knows. This is not a comfortable position for physics to be in. Physics has been extraordinarily successful for several centuries. It has built a framework that describes everything from subatomic particles to the large-scale structure of the cosmos. This is one of the themes of the journey. Every time physics reaches a new scale, familiar words keep working for a while, and then they begin to ask for new meanings. To admit that at the very foundation, at the very deepest level, we simply do not know what is going on is humbling. But it is honest, and honesty about what we do not know is the starting point for finding out. There is a practical dimension to the Planck length that goes beyond pure theoretical interest. The Planck scale is where our current physical theories must be replaced by something better. And understanding that replacement is not just an abstract intellectual exercise, it has consequences. It could tell us why the fundamental constants have the values they do. It could explain the cosmological constant problem, why the vacuum energy is so much smaller than quantum field theory predicts. It could explain why there are 3 generations of quarks and leptons. It could reveal whether the constants of nature could have been different, whether other universes with different constants are possible, whether there is a landscape of possible universes, or whether our universe's parameters are uniquely determined by some deep principle. It could tell us about the ultimate fate of the universe. In the very far future, after all the stars have gone out and all the black holes have evaporated, what remains? The answer depends on the nature of spacetime at the Planck scale, whether spacetime persists indefinitely or whether it eventually dissolves into something else. These questions sound philosophical, but they're deeply physical. They have definite answers determined by the laws of nature. We just do not know what those laws are at the relevant scales. A complete theory of quantum gravity would answer them, or at least it would tell us which questions are genuinely meaningful and which ones do not have answers because they're poorly posed. The Planck scale is not just a curiosity, it is the key that unlocks the deepest questions in all of physics. The questions about the nature of space and time, the origin of the universe, the ultimate structure of matter, the possibility of other realities. All of them converge at the Planck length. All of them will require understanding what happens there to fully answer. Consider what the Planck length tells us about the nature of mathematics and its relationship to physics. We live in a period when physics and mathematics have an extraordinarily intimate relationship. The development of quantum mechanics required inventing new mathematics, or rather using mathematics that had been developed by pure mathematicians for purely abstract reasons, and finding that it described physical reality with astonishing precision in the quiet language of this episode. That is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. Matrices, first developed by Arthur Cayley in the 19th century for purely algebraic reasons, turned out to be exactly the right mathematical language for quantum mechanics. Riemannian geometry, developed by Bernhard Riemann in the 1850s as a generalization of Euclidean geometry to curved spaces, turned out to be exactly the right mathematical language for general relativity. Fiber bundles, developed in the 1940s and 50s as an abstract tool in algebraic topology, turned out to be the right mathematical framework for gauge theories and the Standard Model. In each case, mathematicians had developed the tools before physicists needed them, not knowing they would be needed, not working toward physical applications. Just following the logic of mathematics wherever it led, and physics followed behind, finding that the abstract mathematical structures were already waiting when they were needed. This is one of the great mysteries of the relationship between mathematics and physical reality. Why should the universe be described by abstract mathematical structures that humans invented for reasons having nothing to do with physics? Eugene Venner called it the unreasonable effectiveness of mathematics. The question has never been fully answered, but it suggests that mathematics and physical reality are intimately connected at a level we do not fully understand. And the Planck scale is where that connection may be most fundamental. The Planck length is a pure mathematical quantity derived from the constants of nature. It is the answer to a mathematical question: at what scale do quantum mechanics, gravity, and the geometry of spacetime all become simultaneously important? The mathematics says the Planck length and the physics seems to agree. The Planck scale is where the mathematics of physics breaks down and must be replaced by new mathematics. Whatever that new mathematics turns out to be, it will describe the quantum nature of spacetime. It will describe what space and time actually are at the deepest level. And it may reveal something about why mathematics and physics are connected in the way they are. Why the universe is, as Galileo put it, written in the language of mathematics. The Planck length is, in some sense, the signature of mathematics at the bottom of reality. The place where physical reasoning and mathematical reasoning converge most completely. Where the question of what exists and the question of what is mathematically consistent are closest to being the same question. There is something genuinely beautiful about how the Planck length emerges. Planck wasn't trying to find the fundamental scale of nature. He was trying to fix a broken formula, a formula that classical physics gave him that was provably wrong in the ultraviolet regime. He introduced a mathematical device, the quantum of action, to patch the formula. And then he noticed something in the margins. His patching constant, combined with two other constants that weren't mysterious at all, but were just the constants of gravity and light, produced a length, a universal length, a length that no culture, no species, no civilization anywhere could avoid deriving if they got far enough in physics. The important thing is not to imagine a hard little brick of space. The better image is a boundary in our understanding, a place where smooth geometry and quantum uncertainty can no longer be separated. Because the constants are fixed, they're fixed by the structure of the universe. Any civilization that discovers general relativity will know g. Any civilization that discovers the constancy of the speed of light will know c. Any civilization that discovers the quantum nature of energy will know h. Combine them, and you always get the same number, 1.6. 6 times 10 to the power of minus 35 meters. There is no choice involved. No convention, no human fingerprints. The number is the universe talking. It is the universe naming its own fundamental scale, pointing at the place where the physics we have built needs to be replaced, where the questions get harder and the answers require frameworks that have not been invented yet, where in a very real sense, the universe stops making sense in the terms we currently use and starts making sense in terms we have not yet learned. Planck didn't know any of this. When he wrote down his constant in 1900, he knew he'd solved a practical problem. He suspected he'd done something important. He couldn't have guessed that he was writing down a signpost to the frontier of human knowledge, a boundary marker at the edge of the knowable, the smallest length that can have meaning, the place where space itself stops making sense. The history of physics is not just a history of answers. It is a history of discovering the right questions. Aristotle asked the wrong question about motion and spent centuries getting wrong answers. He asked, "What makes things move?" His answer was that objects seek their natural place. Heavy things fall because they seek the earth. Light things rise because they seek the heavens. This was the wrong framework entirely. The right question was not what makes things move, but what makes things change their motion. That shift in the question from motion to change of motion was what Newton needed to formulate his laws. And once the question was framed correctly, the answer followed. The history of the atom followed a similar pattern. For most of scientific history, people asked what matter is made of. The answer kept getting reframed. Molecules, atoms, electrons and nuclei, protons and neutrons, quarks. Each time the answer seemed like the end, a new question emerged. What are those made of? The question of what lies below the quark, below the electron at the Planck scale, is the current frontier of that thread. and the answer may require changing the question again. Not just asking what the smallest particle is, but questioning whether the concept of particle is the right way to think about it at all. String theory replaces particles with extended objects. Loop quantum gravity questions whether space-time itself is fundamental. Other approaches question whether space and time are the right fundamental variables at all. Twistor theory, developed by Roger Penrose, starting in the 1960s, reformulates physics in terms of different fundamental objects called twistors, which are naturally adapted to the causal structure of spacetime. In twistor theory, the points of spacetime are derived quantities. They're not fundamental. They emerge from more primitive objects, the individual points of spacetime. The very fabric of space and time arise from a more fundamental description. This kind of restructuring of what counts as fundamental is exactly what may be needed at the Planck scale. The universe at the deepest level may not be made of particles moving through space. It may be made of something else entirely, something that produces the appearance of particles and space at larger scales, but that is different in character at the Planck scale. What that something else is, nobody currently knows. This is not a comfortable position for physics to be in. Physics has been extraordinarily successful for several centuries. It has built a framework that describes everything from subatomic particles to the large-scale structure of the cosmos. To admit that at the very foundation, at the very deepest level, we simply do not know what is going on is humbling. But it is honest, and honesty about what we do not know is the starting point for finding out. There is a recurring pattern in the history of physics that's worth recognizing. Each time we have encountered a fundamental breakdown of our theories, the resolution has required giving up something that seemed obviously, necessarily true. Something that felt so basic it couldn't be questioned. In the late 19th century, the equations of Maxwell's electromagnetism conflicted with Newtonian mechanics. They implied that the speed of light was the same for all observers, regardless of their own speed. That seemed impossible. Everyone knew that speeds added. If you are on a train moving at 100 kilometers and you throw a ball forward at 50 kilometers, the ball moves at 150 kilometers an hour relative to the ground, obviously. Obviously, until Einstein pointed out that the obvious thing was wrong. At speeds approaching the speed of light, velocities do not simply add. And more fundamentally, the reason they do not add is that time itself is not absolute. Different observers moving at different velocities experience time passing at different rates. The thing that had to be given up was absolute time. The Newton-Galilean idea that time passes at the same rate everywhere for everyone, regardless of motion. This seemed so obviously true that it wasn't even a scientific claim. It was just assumed. When it was abandoned, the conflict between Maxwell and Newton was resolved. Special relativity made sense of both. Then came the conflict between classical mechanics and the stability of atoms. In the quiet language of this episode, that is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. Seen this way, the Planck length is less like the end of a road and more like a misty shoreline. The land behind us is measured space. The water ahead is quantum gravity. If electrons orbit nuclei like planets orbit the sun, they should radiate energy continuously, spiral inward and crash into the nucleus in a fraction of a nancond. Obviously, atoms are stable. But why the resolution required giving up the idea that physical quantities can take any continuous value? Energy, angular momentum, the orbital states of electrons, all of them are quantized. They come in discrete units. The assumption that had to be abandoned was the continuity of physical quantities. Once quantum mechanics was accepted, atoms were stable. The photon frequencies emitted by hydrogen were predicted exactly. Chemistry made sense at a fundamental level for the first time. Each of these conceptual revolutions required physicists to hold something dear and then let it go. Absolute time, continuous energy, definite trajectories. Each one felt at the time like giving up something obvious, something that surely must be true, but wasn't. Quantum gravity will almost certainly require another such revolution. Something we currently take for granted about the nature of reality will have to be abandoned. The smoothness of space, the continuity of time, the independence of spacetime from quantum fields, the distinction between the observer and the observed at macroscopic scales. Something we do not yet know what, but the history says be prepared for it to be something obvious. Something so obvious that it is hard to even formulate the possibility of giving it up. The Planck length is the place where that giving up will be necessary, where the new framework must take over from the old, where the obvious thing turns out to be wrong again. The cosmological constant problem deserves more attention than it usually gets. It is not just a theoretical puzzle. It is the largest quantitative failure of physical prediction in the history of science, and it is almost certainly connected to what happens at the Planck scale. When quantum field theory is used to calculate the energy density of the vacuum, the result depends on where you set the upper limit of the calculation. The vacuum is filled with virtual particles flickering in and out of existence. All types of particles contribute electrons and positrons, quarks and antiquarks, photons, W and Z bosons, Higgs bosons, and their contributions to the vacuum energy grow with energy. Higher energy virtual particles make larger contributions. If you trust the calculation all the way up to the Planck energy, the predicted vacuum energy density is approximately 1 in Planck units. 1 Planck energy per Planck volume. Now, Einstein's general relativity says that energy density, any energy density, including vacuum energy, contributes to the space-time curvature. It acts like a cosmological constant, and the cosmological constant affects how the universe expands. A very large positive cosmological constant would cause the universe to expand extremely rapidly. So rapidly that matter couldn't clump together, galaxies couldn't form, stars couldn't form, life couldn't arise. The universe would be a thin, cold, featureless gas expanding exponentially forever. Clearly, that's not the universe we live in, so something is canceling almost all of the predicted vacuum energy. The observed cosmological constant determined from the accelerating expansion of the universe discovered in 1998 is approximately 10 to the power of minus 23 in Planck units. The cancellation between the predicted value and the observed value is precise to 123 decimal places. There is no known reason for this. No symmetry produces it. Supersymmetry. A proposed symmetry between bosons and fermions would cancel the vacuum energy contributions if the bosons and fermions came in exactly paired masses. But supersymmetry must be broken because the standard model bosons and fermions have different masses. A broken supersymmetry does not cancel the vacuum energy, it just reduces it somewhat. Not by the required 123 orders of magnitude. The cosmological constant problem is sometimes called the worst prediction in the history of physics. But that framing is slightly misleading. It is not really a prediction. It is a calculation that uses quantum field theory in a regime where we do not actually know the theory is valid. We're using quantum field theory up to the Planck scale, but we do not have a theory of what happens at the Planck scale. Our quantum field theories are effective field theories. They're valid below some cutoff energy. At the cutoff energy, new physics kicks in, new physics that we do not know yet. And that new physics might change the vacuum energy calculation entirely. The cosmological constant problem is, in this sense, a symptom of our ignorance of Planck scale physics. The answer almost certainly lives at the Planck scale, in whatever theory of quantum gravity eventually describes that regime. Which means that understanding the Planck scale is not just a matter of theoretical curiosity. It is the key to explaining why the universe has the cosmological constant it does, why the universe exists in a form where galaxies and stars and life are possible rather than being blown apart by an enormous vacuum energy before any structure could form. The Planck length also appears in unexpected places within physics. One of the most striking is the entropy of black holes. In the early 1970s, Jacob Bekenstein and Stephen Hawking made a remarkable discovery. Black holes have entropy, not just matter, not just radiation. Black holes themselves carry entropy proportional to the area of their event horizons. We will keep the language gentle, but the idea itself is deep. At the smallest meaningful distances, the universe may not offer a smaller stage to stand on. Specifically, the entropy of a black hole equals the area of its event horizon divided by 4 times the Planck length squared times Boltzmann's constant. The Bekenstein-Hawking entropy formula. This result is profoundly puzzling. In ordinary thermodynamics, entropy is a measure of the number of microscopic configurations that correspond to a given macroscopic state. Hot gas has high entropy because there are enormous numbers of ways to arrange the gas molecules while keeping the same total temperature and pressure. A crystal has low entropy because the arrangement of atoms is highly constrained. If black holes have entropy, then there must be a corresponding number of microscopic configurations of the black hole. But what are those configurations? What are the microscopic degrees of freedom of a black hole that give rise to its entropy? General relativity treats a black hole as a smooth object characterized by just 3 numbers: mass, charge, and angular momentum. That's it. There are no microscopic degrees of freedom in general relativity. And yet, the Bekenstein-Hawking entropy can be astronomically large. A solar mass black hole has an entropy of roughly 10 to the power of 77 in dimensionless units. That corresponds to 10 to the power of 10 to the 77 different microscopic configurations. A number so large, it is essentially meaningless to try to comprehend. Any candidate theory of quantum gravity must explain those microscopic configurations, must identify the underlying degrees of freedom that give rise to the Bekenstein-Hawking entropy. This is the black hole entropy problem, or the black hole information paradox in its statistical mechanics form. String theory has had some success with this. In 1996, Andrew Strominger and Kamran Vafa calculated the microscopic entropy of a special class of black holes called extraterrestrial black holes using string theory methods. They counted the number of different string theory configurations that correspond to the same black hole and found it matched the Bekenstein-Hawking prediction exactly. This was a major victory for string theory. Not an experimental test, but a calculation of something that no other framework could calculate, giving the right answer. Loop quantum gravity has also addressed this. Carlo Rovelli and Kirill Krasnov computed the entropy of black holes in loop quantum gravity by counting the number of spin network states that correspond to a given black hole area. They also found agreement with the Bekenstein-Hawking formula up to the value of the Barbero-Emirzi parameter. Both approaches agree that the microscopic degrees of freedom of a black hole are associated with the Planck scale structure of the event horizon. Each Planck area of horizon surface carries one bit of information, roughly 1 unit of entropy. The Bekenstein-Hawking entropy is literally the area of the horizon measured in Planck units divided by 4, which means that the information content of a black hole, the number of physical states it can be in scales with the area of its surface, not the volume of its interior. This is the holographic principle. The information in a three-dimensional region of space can be encoded on its two-dimensional boundary and the fundamental unit of information. The bit corresponds to 1 Planck area of boundary surface in the quiet language of this episode. That is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. The holographic principle discovered by Gerard T. Hooft and Leonard Susskind in the early 1990s suggests something profound. The three-dimensional volume of space that we experience may not be fundamental. The fundamental description of reality may be two-dimensional, a hologram. The three-dimensional world inside the hologram is in some sense an illusion, a projection of a more fundamental two-dimensional reality. In string theory, the ADS-CFT correspondence of 1 Maldacena provides a concrete realization of this. A gravitational theory in a certain kind of curved spacetime is mathematically equivalent to a quantum field theory without gravity on the boundary of that spacetime. The boundary lives in one fewer dimension, and the boundary theory is the more fundamental description. All of this connects back to the Planck length, the fundamental unit of information. The fundamental unit of entropy is 1 Planck area. The holographic principle, the deepest structure of black hole thermodynamics. All of it is written in units of the Planck length. The Planck length is not just the scale at which our theories break down. It is the fundamental unit of the deep information theoretic structure of spacetime. There is a question that naturally arises: why these particular values for the fundamental constants? Why is Planck's constant 6.626 times 10 to the power of minus 34 seconds? Why is the gravitational constant 6.67 times 10 to the power of minus 1 meters per kilometers per second squared? Why is the speed of light 2.998 times 10 to the power of 8 meters per second? These values seem arbitrary. They could, as far as we can tell, have been different. And if they had been different, the Planck length would be different. The fundamental scale of quantum gravity would be different. The properties of atoms, the strengths of chemical bonds, the mass of the electron, the stability of the proton, all of these depend on the values of the fundamental constants. Change the constants even slightly, and the universe would look very different. Change the fine structure constant, which determines the strength of electromagnetism, by a factor of a few, and atoms as we know them wouldn't be stable. Change the strong coupling constant by a fraction, and the proton would be unstable, or nuclear physics would be different enough that the periodic table of elements wouldn't form in the same way. Change the cosmological constant by even a small amount, and either the universe would have collapsed back on itself before galaxies could form, or expanded so rapidly that matter couldn't clump. Let us move through this slowly, because the smallness here is not only a matter of size, it is a change in what size can mean. This sensitivity of the universe's structure to the values of the fundamental constants is called the fine-tuning problem, or in its most anthropic formulation, the question of why the constants are compatible with life. The various approaches to quantum gravity have different things to say about this. String theory, with its landscape of 10 to the power of 500 possible vacuum states, suggests that there may be a vast ensemble of universes with different values of the constants. We find ourselves in one where the constants are compatible with our existence. Not because those values were chosen, but because only in such universes could observers arise to notice. This anthropic reasoning is controversial among physicists. Some find it compelling, others find it untestable and therefore unscientific. The debate is ongoing. Loop, quantum gravity, and most other approaches do not naturally produce a multiverse of this kind. They typically treat the constants as inputs to be determined by experiment, not by anthropic selection. But some physicists hope that a complete theory of quantum gravity might actually predict the values of the fundamental constants, that there might be only one mathematically consistent theory of everything, and that theory might fix the constants uniquely. If that were true, the apparent fine-tuning would turn out not to be fine-tuning at all. The constants wouldn't have been chosen. They would be the only possible values. The universe would be the only possible universe. This is an ambitious hope, and there is no current evidence that any candidate theory of quantum gravity is unique in this way. But it is a coherent scientific aspiration, and understanding the Planck scale, where the constants combine to produce the fundamental unit of length, is central to this aspiration. The Planck length is the fingerprint of the fundamental constants. Understanding it deeply means understanding why those constants have the values they do, which is one of the deepest questions in science. Something worth dwelling on is how accessible the Planck length actually is in the right sense. You cannot touch it, you cannot see it, you cannot build an instrument that probes it. But you can derive it with a few constants written on a piece of paper and a calculation that takes about a minute. You can write down the fundamental scale of quantum gravity. The smallest meaningful distance in the universe, the Planck length. This is one of the remarkable things about physics. The most inaccessible scales in nature can be derived from the most accessible measurements. Planck's constant was measured in laboratory experiments, most famously the photoelectric effect studied by Einstein in 1905. The gravitational constant was measured by Henry Cavendish in 1798 using a torsion balance, 2 small masses and 2 large masses, and the tiny gravitational attraction between them. The speed of light was measured by Ole Romer in 1676 by timing the eclipses of Jupiter's moon Io and noting that they arrived early or late depending on the position of Earth in its proof orbit. The fundamental measurements were made with everyday laboratory equipment, pendulums, lenses, wires, weights, and from those measurements you can derive the smallest possible length, the scale of quantum gravity, the frontier of physics. This accessibility of derivation, despite inaccessibility of probe, is one of the most striking features of the Planck length. It tells you that the fundamental scales of nature are not hidden behind arbitrary choices or human conventions. They're written directly in the constants of nature, available to anyone who does the calculation. Any physicist anywhere in the universe doing the equivalent experiments and working out the same constants would derive the same Planck length, because the Planck length does not depend on human conventions. It depends on the structure of the universe. This universality was what struck Planck when he first computed it. He was not given to making dramatic announcements. He was methodical, careful, conservative. But he described the natural units as retaining their meaning for all time and for all civilizations, even extraterrestrial ones. This was not a casual remark. It was a recognition that he had found something fundamental, something that wasn't a property of his instruments or his culture or even his species, a property of nature itself. The Planck length is where nature writes its most fundamental scale. The uncertainty principle plays a central role in all of this, and it deserves a moment of deeper examination. Heisenberg formulated the uncertainty principle in 1927. The famous position-momentum form says that the product of the uncertainty in position and the uncertainty in momentum must be at least h bar divided by 2. But there is another form that's equally important for understanding the Planck scale, the energy-time uncertainty relation. The uncertainty in energy multiplied by the uncertainty in time must be at least h bar divided by 2. This has a remarkable consequence. On very short time scales, large amounts of energy can be uncertain. For a time interval of roughly 1 Planck time, approximately 5.44 times 10 to the power of minus 44 seconds. The uncertainty in energy is approximately the Planck energy, roughly 1.2 times 10 to the power of 28 electron volts. This is one of the themes of the journey. Every time physics reaches a new scale, familiar words keep working for a while, and then they begin to ask for new meanings. This means that on time scales shorter than the Planck time, energy fluctuations are as large as the Planck energy. And the Planck energy concentrated in a Planck scale region produces a black hole. So, on subplan timescales, spacetime is subject to fluctuations energetic enough to spontaneously create and destroy black holes. The geometry of space is not just fluctuating mildly, it is fluctuating so violently that the topology itself may be constantly changing. Black holes appearing and evaporating, wormholes forming and closing, space connecting and disconnecting. All on timescales shorter than the Planck time, this is Wheeler's quantum foam quantified, not just a qualitative picture. A consequence of applying the uncertainty principle to the geometry of spacetime. In the quiet language of this episode, that is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. Above the Planck scale, these fluctuations are subdominant. They're corrections to an otherwise smooth geometry. But at below the Planck scale, they're not corrections. They're the dominant feature. They swamp the classical geometry entirely. The smooth space-time of everyday experience does not exist there. What exists, if the word exists, can even be used is a quantum superposition of wildly different geometries, a foam of possibilities. And we observe the classical smooth geometry, not because that's the underlying reality, but because we are always averaging over an enormous number of Planck scale fluctuations. We're seeing the average, the classical geometry, is the long-term, large-scale average of a microscopic quantum chaos. Just as the smooth blue sky is the average of an enormous number of individual photon scatterings from molecules and particles, the individual events are not smooth. The average is there is a beautiful irony in the history of the Planck scale. The person who discovered it, Max Planck, was one of the most reluctant revolutionaries in the history of science. He introduced the quantum not because he thought energy was really discrete. He introduced it because he needed a mathematical trick to make his formula work. He spent years trying to find a way to derive his black body formula without assuming genuine discreteness. He failed, but the revolutionary implications were developed by others. Einstein in 1905 used Planck's quantum to explain the photoelectric effect and proposed that light itself consists of discrete photons. This was radical. Even Planck resisted it. Bohr in 1913 used Planck's quantum to explain the structure of the hydrogen atom. Heisenberg in 1925 built the first complete formulation of quantum mechanics. Schrödinger in 1926 provided an alternative wave mechanical formulation. Dirac synthesized the two in 1926 and extended quantum mechanics to include special relativity. All of this was built on Planck's constant, but Planck himself was not central to this development. He was a spectator to the revolution his discovery had started. He won the Nobel Prize in 1918 for the discovery of energy quanta. He lived until 1947 and saw quantum mechanics developed into the most successful physical theory in history. He also saw 2 world wars, the rise and fall of the Nazi regime in his country, and the tragic deaths of multiple members of his family. His younger son, Erwin, was executed by the Nazi regime in January 1945 for involvement in the July 20th assassination attempt on Hitler. Planck continued to work and write until near the end of his life. He gave a lecture titled "Science Retains Its Meaning" at the age of 87. He was, by all accounts, a man of extraordinary personal integrity and intellectual honesty. And the constant that bears his name, the constant from which the fundamental length of quantum gravity is derived, is his permanent legacy, not just to physics, to understanding. Because the Planck length is ultimately a statement about the limits of understanding, about where current knowledge ends, about where the next great revolution in physics must begin. And that legacy, the legacy of pointing at the frontier, of showing where the boundaries are, is a gift to every physicist who comes after. There is a thought experiment worth considering. Suppose an alien civilization somewhere in the Milky Way managed to develop physics to a level comparable to ours. They would presumably discover the same constants of nature, the same speed of light, the same gravitational constant, something equivalent to Planck's constant. Because those constants are not human inventions, they're properties of the universe. And they would presumably combine those constants and derive the same Planck length, the same fundamental scale, the same boundary between the describable and the indescribable. They would face the same problem we face, a classical theory of gravity that works beautifully at large scales, a quantum theory of matter that works beautifully at small scales, and an impossible incompatibility between the two at the Planck scale. They would be working on the same problem we are working on, quantum gravity. Maybe they've solved it, maybe they have not. Maybe the problem is hard enough that no civilization has solved it yet. Maybe the problem has a solution that requires mathematics far beyond what any civilization at our level of development can access. We do not know, but the Planck length would be the same, written in the same fundamental constants, pointing to the same frontier. Any sufficiently advanced physics anywhere in the universe encounters the Planck length. It is the most universal number in science, not a human number, a universe number. And it is a number that says, here at this scale you will find something you do not yet understand. Here is where the next chapter begins. Whatever the next chapter contains, it will be written in language we do not yet have, describing structures we have not yet conceived, using mathematics that does not yet exist. The important thing is not to imagine a hard little brick of space. The better image is a boundary in our understanding, a place where smooth geometry and quantum uncertainty can no longer be separated. And when it does exist, when some future physicist or team of physicists or artificially intelligent system or alien civilization cracks the problem, the Planck length will still be there, not as a mystery anymore, but as a boundary that was crossed. The way the speed of sound was a boundary that seemed impenetrable and then wasn't. The way the energy of chemical bonds seemed impenetrable until nuclear physics revealed the energy inside the nucleus. The way the ultraviolet catastrophe seemed like the end of classical physics and turned out to be the beginning of the quantum era. Every apparent wall turns out eventually to be a doorway. The Planck length is the next doorway, and we are standing in front of it, knocking, not yet sure what is on the other side. There is a corner of the story that rarely gets told in the popular accounts. The history of how we learned that matter had a minimum structure, not just the Planck length, but every step on the way there. Because understanding where we are going requires understanding how many times we thought we'd already arrived. For most of human history, the question of whether matter could be divided indefinitely was a philosophical argument, not a scientific one. Democritus and Leucippus, Greek philosophers in the 5th century B.C., proposed that matter consisted of fundamental, indivisible units they called atomos. Their argument was elegant in its simplicity. If you keep dividing matter, eventually you must reach something you cannot divide further. Otherwise, division goes on forever, and the structure of matter would be infinitely complex all the way down. Democritus concluded that there had to be a bottom, the smallest thing. His contemporaries largely dismissed this view. Aristotle, who had more influence on subsequent scientific thinking than almost anyone else in history, believed matter was continuous, infinitely divisible, no bottom. Aristotle won. For nearly 2,000 years, atomism was a minority view held by philosophers outside the mainstream. The idea of atoms didn't make serious scientific progress until John Dalton, an English chemist working in the early 19th century, began to notice patterns in how chemical elements combine. When hydrogen and oxygen combine to form water, they always do so in the same proportion by mass. 8 g of oxygen for every 1 g of hydrogen. When carbon and oxygen combine to form carbon dioxide, the ratio is again fixed. 12 g of carbon for every 32 g of oxygen. These fixed ratios made sense only if matter consisted of discrete particles combining in definite proportions. 1 atom of oxygen for every 2 atoms of hydrogen. 1 atom of carbon for every 2 atoms of oxygen. Dalton published his atomic theory in 1803. He could not see atoms directly, no one could. But the patterns in chemistry demanded their existence. This is one of the oldest patterns in physics. You infer the existence of something you cannot directly see from the behavior of things you can. The same logic that led Dalton to atoms from chemical proportions would later lead physicists to quarks from the patterns of particle collisions. And the same logic leads theoretical physicists today to suspect that there is a minimum scale of spacetime from the mathematical patterns in the equations of quantum gravity. You do not need to see the thing directly, you need the thing to be the only explanation for what you can see. Dalton's atomic theory was vindicated repeatedly over the 19th century. The development of the kinetic theory of gases, which explained the pressure and temperature of gases as the result of enormous numbers of atoms in constant motion, put atoms on firmer mathematical footing. James Clerk Maxwell and Levi Boltzmann worked out the statistical mechanics of gases using atoms as the fundamental units. Their equations predicted the specific heat capacities of gases, the diffusion rates of different substances, and the viscosity of fluids. In the quiet language of this episode, that is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. All from the assumption that matter consisted of discrete particles. But well into the late 19th century, many physicists still resisted the atomic hypothesis. Ernst Mach, one of the most influential physicists and philosophers of science of the era, rejected atoms on positivist grounds. You cannot directly observe them, he argued, therefore, you should not include them in your physical theories. Mach's position was coherent but ultimately wrong. The turning point came from an unexpected direction. In 1905, Einstein published 5 remarkable papers. 3 of them were individually worth a Nobel Prize. One described the photoelectric effect and introduced the idea that light came in discrete packets, the photons. One was the special theory of relativity. But the third, often overlooked in the hagiography of that year, explained the phenomenon of Brownian motion. Brownian motion is the random, jittery movement of small particles suspended in a fluid. If you look at a dust particle suspended in water under a microscope, it moves not smoothly, not directionally, in a constant, random, unpredictable zigzag. This had been observed by the Scottish botanist Robert Brown in 1827. He initially thought it might be a sign of life in the particles. It wasn't. Inorganic dust particles did it too. Nobody had a good explanation. Einstein showed that Brownian motion was exactly what you'd expect if water consisted of enormous numbers of discrete molecules constantly colliding with the suspended particle. Each collision gave the particle a tiny push in some random direction. Seen this way, the Planck length is less like the end of a road and more like a misty shoreline. The land behind us is measured space. The water ahead is quantum gravity. The accumulated effect of billions of such collisions per second produced the observable jitter. And crucially, Einstein's theory made quantitative predictions. It predicted how far the particle would move on average in a given time. It predicted how that distance depended on temperature and on the size of the particles. The French physicist Jean Perrin measured all of these things and found that Einstein's predictions were correct to experimental precision. Mach had been wrong. Atoms were real. Discrete matter was real. The century-old debate between atomism and the continuum was settled definitively in favor of the discrete. And the lesson of that story is important for the Planck length. The existence of atoms was inferred long before atoms could be directly seen. The evidence was indirect. The argument was mathematical. The confirmation took over a century. And when it came not from seeing atoms, but from seeing the statistical effects of enormous numbers of them. The story of the Planck length may follow a similar arc. We cannot directly probe it. We may never directly probe it, but the indirect evidence, the patterns in the equations, the convergence of multiple independent frameworks, the experimental constraints from astronomical observations may eventually build to the point where the conclusion is inescapable. The way the conclusion about atoms eventually became inescapable, not certainty through direct observation. Certainty through the accumulation of mathematical and observational evidence too consistent to be coincidental. There is a number that haunts modern physics more than almost any other. It is called the fine structure constant, and it is usually written as the Greek letter alpha. Its value is approximately 1 divided by 137. More precisely, 0.007297356. This number determines the strength of the electromagnetic interaction. It tells you how strongly electrons interact with photons. It is dimensionless, which means it has no units. It is a pure number. No kilograms, no meters, no seconds, just a number, and nobody knows where it comes from. The fine structure constant appears everywhere in atomic physics. It determines the energy levels of electrons in atoms. It determines the rate at which atoms emit light. It determines the splitting of spectral lines when atoms are placed in magnetic fields. Without the precise value of the fine structure constant, chemistry as we know it would not exist. If alpha were significantly larger, the electromagnetic force between electrons in atoms would be stronger, atoms would be smaller, and the chemistry of carbon, which underlies all known life, would work very differently. If alpha were significantly smaller, electrons would be more weakly bound and atoms would be more diffuse. The specific value 1/137 appears to be exactly right for the kind of chemistry that produces complex molecules, cells, and ultimately observers who wonder about physics. Richard Feynman, one of the great physicists of the 20th century, called the fine structure constant, a magic number that comes to us with no understanding. He said that all good theoretical physicists put this number up on their wall and worry about it. The number 137 is not special in mathematics. It is a prime number, but being prime has no obvious physical significance. It is not pi. It is not the golden ratio. It is not obviously derived from any mathematical structure we know of. It simply is what it is, and we do not know why. The Planck length connects to this puzzle in a deep way. The Planck length is built from 3 constants, but the fine structure constant is not among them. The fine structure constant involves the charge of the electron, the speed of light, and Planck's constant. Planck's constant appears in the Planck length. The speed of light appears in the Planck length, but the electron charge does not. Which means the Planck length and the fine structure constant are built from overlapping but not identical ingredients. They describe different aspects of nature's fundamental structure, And this raises a question that has no answer yet. Why do these particular constants have these particular values? Why is Planck's constant 6.626 times 10 to the power of minus 34 joule seconds? Why is G 6.67 times 10 to the power of minus 1? Why is the speed of light exactly 2.9979245 times 10 to the power of 8 meters per second? Why is alpha 1 over 137 and not 1 over 138? There are two broad philosophical positions on this question. The first is that there will eventually be a theory that explains these values from deeper principles. That there is some mathematical structure not yet discovered from which the constants of nature can be derived. The way the ratios of distances in the solar system were once hoped to follow from Kepler's model of nested platonic solids, though that turned out to be wrong, or the way the mass of the electron can, in principle, be calculated from quantum field theory using the concept of renormalization. Though in practice, this calculation requires knowing other constants as inputs. The second position is that the constants are what they are by chance or by selection. In a universe with a vast landscape of possible values for the constants, perhaps only certain combinations are compatible with the existence of observers who can ask the question. This is the anthropic principle. The observation that the constants of nature appear fine-tuned for life could, on this view, be explained by the fact that only in universes with roughly these constants does anyone exist to notice the fine-tuning. String theory provides a possible mechanism for this. The enormous landscape of possible solutions, estimated at around 10 to the power of 500 different configurations, means that if all these configurations are realized in some sense, perhaps through an inflationary multiverse, the values of the constants vary across the landscape. We find ourselves in a pocket with these values because these values are compatible with our existence. We will keep the language gentle, but the idea itself is deep. At the smallest meaningful distances, the universe may not offer a smaller stage to stand on. The debate between these positions is fierce and unresolved. Some physicists find the anthropic argument compelling. Others find it deeply unsatisfying, a pseudo-explanation that explains everything and therefore explains nothing. What the Planck length tells us is that whatever the explanation turns out to be, the value matters. Change the constants and the Planck length changes. A different Planck's constant, a different gravitational constant, a different speed of light, and you get a different minimum scale for spacetime. Possibly a minimum scale so large that atoms couldn't exist above it. Possibly a minimum scale so small that the theory of quantum gravity would look completely different. The Planck length is one of the signatures of the specific set of constants that our universe has chosen or been dealt or had forced upon it by some deeper mathematical necessity we have not yet found. It is one of the numbers that tells you what kind of universe you are in, and it is pointing us insistently toward the deeper physics that underlies it. There is one more piece of the Planck story that deserves attention, and it involves black holes. Not the supermassive black holes at the centers of galaxies, billions of times the mass of the Sun. Not even stellar mass black holes, the remnants of collapsed stars, but hypothetical objects at the other end of the scale. Black holes with mass close to the Planck mass. The Planck mass is what you get when you combine h bar, g, and c in the appropriate way. It works out to approximately 2.17 times 10 to the power of minus 8 kilograms. That's about 22 microgram, the mass of a small grain of sand or a few hundred cells of your body. A black hole with a mass close to the Planck mass would have a Schwartz radius close to the Planck length. It would be the smallest possible black hole, and it would be subject to something that Stephen Hawking discovered in 1974. In the quiet language of this episode, that is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. Hawking radiation. Before Hawking's result, it was assumed that black holes could only grow, matter falls in. Nothing comes out. The mass of a black hole increases monotonically. Hawking showed that this was wrong. The quantum mechanical vacuum, even near a black hole, is not truly empty. Quantum fluctuations produce pairs of virtual particles, a particle and its antiparticle, on timescales so short that the uncertainty principle permits it. Near the event horizon of a black hole, something strange can happen. One of the virtual particles falls into the black hole, the other escapes. The escaping particle carries energy, and that energy has to come from somewhere. It comes from the black hole itself. The black hole loses mass. The rate of this mass loss, the Hawking temperature of the black hole, is inversely proportional to the mass of the black hole. Small black holes are hotter than large ones. A black hole with the mass of the Sun would have a Hawking temperature of about 60 nanokelvin, much colder than the cosmic microwave background. It would actually absorb radiation from the background faster than it emitted Hawking radiation. So it would grow, not shrink. A black hole with the mass of a mountain around 10 to the power of 12 kilograms would have a temperature of about 10 to the power of minus 14 Kelvin. Still cold. But a black hole with a mass close to the Planck mass would have a Hawking temperature close to the Planck temperature over 1.4 times 10 to the power of 32 Kelvin. And a black hole at the Planck temperature is evaporating at the maximum possible rate. The final moments of a black hole's evaporation as it shrinks toward the Planck mass are described by physics we do not fully understand. What happens to a black hole when it reaches the Planck scale? Does it evaporate completely, leaving nothing behind? Does it leave some kind of stable remnant, a Planck mass relic that cannot shrink further because there is no smaller black hole possible? Does the information about everything that fell into the black hole over its lifetime somehow escape in the final burst of Hawking radiation? This last question is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Quantum mechanics insists that information cannot be destroyed. If you burn a book, in principle, you can reconstruct all the information in the book from the photons and gases that the burning produces. The information is scrambled but not erased, but black holes seem to destroy information. Matter with specific properties falls in, Hawking radiation comes out, and it is thermal, random. No information about what fell in. If the black hole evaporates completely, where does the information go? Hawking himself originally argued that it was destroyed, that black holes violated the quantum mechanical principle of information conservation. Most physicists were deeply unhappy with this conclusion. It required modifying the foundations of quantum mechanics, which seemed too high a price to pay. Over the following decades, evidence accumulated from string theory and from the study of black hole entropy that information is not destroyed. That somehow, in a way we do not fully understand, the Hawking radiation encodes information about everything that fell in. The resolution likely involves physics at or near the Planck scale, where the quantum and gravitational descriptions must be reconciled. The holographic principle developed in the 1990s from the work of Gerard T. Hooft and Leonard Susskind suggests that the information content of any region of space is encoded on the boundary of that region at a density of 1 bit per Planck area. 1 bit per roughly 1 Planck length squared. This is the Bekenstein-Hawking entropy formula for black holes. The entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck area. This formula, discovered by Jacob Bekenstein and refined by Hawking, is one of the most important results in theoretical physics. It connects thermodynamics, quantum mechanics, and gravity in a single equation, and the Planck length appears in it as the fundamental unit. Let us move through this slowly, because the smallness here is not only a matter of size, it is a change in what size can mean. The fact that information is stored at a density of 1 bit per Planck area suggests that the Planck area is not just a minimum unit of spatial area in loop quantum gravity. It may be a fundamental unit of information storage in any complete theory of quantum gravity. Space itself in this picture is information arranged in discrete Planck Scale pixels, each pixel storing 1 bit. The smooth, continuous space you experience is an emergent picture assembled from an enormous number of these bits. The way a high-resolution image on a screen looks smooth until you zoom in enough to see the individual pixels. At the Planck scale, you'd see the pixels and what the pixels are made of. What it means for a region of space-time to store 1 bit of information is a question that the physics we have can gesture toward, but not yet answer. The scale of time matters as much as the scale of space, and the Planck time is as strange as the Planck length. The Planck time is approximately 5.4 times 10 to the power of -4 seconds. To give you a sense of what that means, the fastest nuclear processes, the decay of certain mesons produced in particle accelerators, happen on timescales of around 10 to the power of 23 seconds. That's already almost incomprehensibly fast, a 100 billion times faster than a billionth of a second. The Planck time is about 20 orders of magnitude shorter than that, a factor of 100 billion. If a single Planck time was scaled up to 1 second, a second would scale up to roughly 300 billion times the age of the universe. The Planck time is to a second as a second is to 30,000 times the current age of the cosmos. These ratios are genuinely hard to hold in your mind. Your brain didn't evolve to handle them. Mine didn't either, but they're real. The Planck time is the shortest duration that has meaning. Below it, the concept of before and after, of one event preceding another, may cease to apply. Think about what that means. Causality, the principle that causes effects, is one of the most basic features of the universe as we experience it. Your coffee cools because of interactions that happen in a sequence. The hot water loses heat to the cooler air around it. One molecule at a time, one interaction at a time, each cause preceding its effect. The whole edifice of physics rests on this ordering. Differential equations, the language of classical physics, describe how a system changes from one instant to the next. The next instant comes after the current one. Causes propagate forward in time. Effects do not precede causes. At the Planck scale, this ordering may become uncertain. The concept of before and after may blur. The sequence of events may become fuzzy at the level of individual Planck time intervals. Now, in everyday life, you are never going to encounter this. The smallest time interval you are personally aware of is probably measured in milliseconds. The smallest time interval that neuroscience suggests can be individually processed by the human brain is roughly 10 milliseconds. The Planck time is 32 orders of magnitude shorter than that, a trillion times smaller. You will never experience the blurring of causality at the Planck time, but it matters for how the universe works at its most fundamental level. It matters for what happened in the first moments after the Big Bang. It matters for whether our intuitions about cause and effect apply to the underlying structure of reality or whether they're emergent properties of the large-scale average. The way temperature is an emergent property that does not apply to individual molecules. The laws of thermodynamics tell you that heat flows from hot to cold, but an individual molecule can move in any direction. The directionality of heat flow is a statistical consequence of the behavior of enormous numbers of molecules. It is emergent, not fundamental. The arrow of time, the fact that the past is different from the future that causes predefects, may similarly be emergent. Something that arises at large scales from a deeper physics that is at the Planck scale time-symmetric, or not merely time-symmetric, but something stranger. A regime where the notion of time ordering does not apply at all. This is deeply counterintuitive and deeply important because if the arrow of time is emergent rather than fundamental, then understanding where the arrow of time comes from, why the universe has a past and a future, why there is a direction to the flow of time at all, requires understanding physics at or near the Planck scale. Requires, in other words, the theory we do not have yet. The Planck time is not just the shortest meaningful duration. It is a marker of the regime where the most basic features of reality, causality, the arrow of time, the structure of before and after may need to be explained rather than assumed, where the foundations of physics need to be rebuilt rather than extended. The Planck length marks the edge of space as we understand it. The Planck time marks the edge of time. Together, they mark the edge of spacetime itself, the edge of the framework within which all known physics operates, in the quiet language of this episode. That is another way of saying that the universe is asking us to change the question before we ask for a smaller answer. And beyond that edge, whatever is there is the next chapter of the story. Physics is full of constants: the charge of the electron, the mass of the proton, the Boltzmann constant, the permittivity of free space. There are dozens of them, and collectively they determine everything about how the physical world works. But most of these constants are not fundamental in the deepest sense. They're combinations of more fundamental things, or they're quantities that depend on choices of units. The mass of the proton in kilograms depends on how you define a kilogram. In a different unit system, it would be a different number. The true constants of nature, the ones that are independent of any choice of units, are dimensionless numbers. This is one of the themes of the journey. Every time physics reaches a new scale, familiar words keep working for a while, and then they begin to ask for new meanings, numbers with no units at all, pure ratios. The fine structure constant 1/137 is one of these. So is the ratio of the mass of the proton to the mass of the electron, which is approximately 1836. So is the ratio of the strengths of the four fundamental forces at any given energy. These dimensionless constants are the most fundamental numbers in physics. Change them, and you change the universe in ways that cannot be disguised by a change of units. Now, the Planck length itself is not dimensionless. It has units of length. But the interesting quantity is the ratio of the Planck length to the size of things we can observe. The ratio of the Planck length to the diameter of a proton is approximately 1 divided by 10 to the power of 20. That's a dimensionless number, a pure ratio. And it reflects the ratio of the strengths of gravity to the strong nuclear force at the scale of a proton. Gravity is extraordinarily weak compared to the other forces. The gravitational force between two protons is about 10 to the power of 36 times weaker than the electromagnetic force between them. This enormous ratio of force strengths is one of the most puzzling features of the Standard Model. It is called the hierarchy problem. Why is gravity so much weaker than the other forces? The Planck length being so much smaller than the proton is another way of stating the same puzzle. If gravity was stronger, the Planck length would be larger. If the Planck length were comparable in size to the proton, the universe would look completely different. Protons would be collapsing into black holes. Stars wouldn't form the way they do, the specific weakness of gravity. The specific smallness of the Planck length relative to atomic scales is one of the things that makes the universe work the way it does. Several theoretical proposals have attempted to explain the hierarchy problem. Supersymmetry, which posits a symmetry between matter particles and force particles, was one of the leading candidates for decades. If supersymmetry exists, it would stabilize the hierarchy by providing cancellations between contributions to certain quantum corrections. But the Large Hadron Collider has searched for supersymmetric particles and has not found them in the mass ranges that the most natural versions of supersymmetry predicted. The parameter space for simple supersymmetry is increasingly constrained. Other proposals include extra dimensions of space, large or small, that would change how gravity behaves at small scales. If there are extra dimensions, the effective Planck length in four-dimensional spacetime could be much larger than the true Planck length in higher dimensions. This is the Randall-Sundam scenario and related models. They predict that gravity could become strong at much larger scales than the conventional Planck length, perhaps even at the energy scales accessible to the Large Hadron Collider. The LHC looked for signatures of extra dimensions and found none. But the constraints have narrowed the possibilities rather than eliminated them. The hierarchy problem remains open. The puzzle of why the Planck length is so much smaller than the scales of ordinary matter remains unsolved. It is another entry on the long list of deep questions that the Planck scale sits at the heart of. Why are the constants what they are? Why is gravity so weak? Why is the Planck length so small? These questions may have answers that are independent, or they may all be connected facets of a single deeper structure. The theory of quantum gravity, whatever form it eventually takes, will need to address all of them. And the Planck length, that specific combination of three constants that Planck wrote down almost as an aside in 1900, will be somewhere near the center of the explanation. Tonight, we went as small as the universe allows. Smaller than atoms, smaller than nuclei, smaller than protons, smaller than quarks, to the very threshold where the fabric of space stops being fabric at all, where time stops being a sequence, where distance loses its definition, where the three deepest constants of nature, the quantum constant, the gravity constant, and the speed of light converge, and write one number that the universe hands to every civilization that ever does physics: 1.6 times 10 to the power of minus 35 meters. The Planck length is not just a small number, it is the point where physics becomes honest about what it does not know, where the map runs out, where the territory is still there unexplored and waiting, where a gap this precise and this well located in our understanding is telling us something extraordinary, that there is a deeper structure waiting to be found, a layer below every layer we know, a language in which the universe is speaking that we have not yet learned to hear. In the history of physics, every time we have reached a boundary like this, we have eventually found a way through. And every time we did, what lay beyond was stranger and more wonderful than anything we'd imagined. There is no reason to believe this time will be different. The Planck length is not the end of the road. It is the sign that the road continues in a direction we have not learned to walk yet. And when you go outside tonight and feel the ground beneath your feet, think about what is underneath. Not just soil and rock, but atoms. And within those atoms, nuclei and electrons. And within those nuclei, quarks, and beneath that, at scales we cannot yet reach, something we understand less. And less the deeper we go, until you reach the frontier. 1.6 times 10 to the power of minus 35 meters from the bottom of everything we know. The important thing is not to imagine a hard little brick of space. The better image is a boundary in our understanding, a place where smooth geometry and quantum uncertainty can no longer be separated. Good night. And so we return. gently from the smallest scale we can name. The room is still here, the chair is still here, the floor still feels smooth beneath the world of ordinary things. But beneath that smoothness, physics has shown us something humbling. Space is not just emptiness. Time is not just a clock. Measurement is not just looking more closely. At the Planck length, every familiar idea arrives carrying another idea inside it. Quantum uncertainty, gravitational curvature, the finite speed of light, and the quiet possibility that geometry itself has a deeper structure. We do not yet know the final theory. We do not know whether strings, loops, holographic boundaries, or some future language will give the clearest picture. But we do know why the question matters. The Planck length marks the place where the universe stops letting our current theories stay apart. It is where the smooth fabric of relativity and the grainy music of quantum mechanics must finally learn to speak together. And perhaps that is the softest way to leave it tonight. At every scale we understand, the universe has given us patterns. At the largest scales, galaxies gather into filaments. At human scales, matter rests in rooms and oceans and mountains. At atomic scales, electrons and nuclei make the chemistry of stars and skin and stone. And at the smallest scale we can meaningfully name, there may be no simple picture left, only the promise that space itself is deeper than it first appears. Rest there for a moment, at the edge of the measurable, where the next answer has not yet become a shape.